Thank you very much, Estella. Good afternoon, ladies and gentlemen. It's a pleasure talking to you today regarding CCD LiDAR ToF. Maybe you know ESPROS as a company which does time-of-flight imager for indirect time-of-flight or CW ToF, but we also do LiDAR imaging based on pulse ToF. Okay, how to go to the next slide? Okay, so that's the plan. Our objective, having a nice evening somewhere, a nice restaurant, and then just tell Siri or the other supporters in the net, drive me home, please. That's what we're working on. So I'm talking about the ADAS requirements, the limitations of current available LiDAR sensors. I'm doing a sensor technology comparison, and then I focus more specifically on the ambient light problem, because ambient light photons compete with the illumination of LiDAR sensors, and they don't really contribute to measurement. And at the end, I'm going to show you some performance data of a PToF imager, so pulse time-of-flight imager we implemented. Okay, you all know the requirements for LiDAR imagers, LiDAR sensors. They vary, and typically they are very high, and they are sometimes quite contradictory. One important point is the resolution. The spatial resolution to achieve a 20 centimeter resolution at 150 meters, you need a spatial resolution which has to be better than 0.05 degrees. And that's quite a killer which has to be addressed somehow. As I said, the specifications, they vary. Depending on who you're asking, what is the requirements of the sensor you are looking for. Typically, if you talk to a German auto manufacturer, they say at least 250 meters, and they want to see a tire, a small piece of a tire on the road, not to run over this debris with 250 kilometers per hour. So that's a quite challenging requirement, but there are also others coming from the robotaxi manufacturers, which they are looking rather into a domain of, let's say, 50 to 100 meters and not at that fast speed. So the comparison here is regarding different technologies. Radar, which basically has a poor spatial resolution, ultrasonic, which is typically for short range. Then CW ToF is typically very high resolution, distance imaging, scanning LiDAR, which suffer on the spatial resolution. And then what we are doing actually is a PToF imaging LiDAR, let's say, small point is a horizontal field of view, 360 degrees. You can only do that by implementing multiple cameras around the car, whereas with a scanning sensor, you can do that in a 360 degree manner. And cost currently is not green yet, but it's a question of the volume to achieve low-cost implementation. As I said, scanning LiDAR systems, they suffer from a poor resolution. Typically 8 or 16 or maybe 64 horizontal lines. Some of them 128, but then it becomes quite expensive. So, and if you want to achieve 0.05 degrees spatial resolution, then you need a vertical resolution in the range of, let's say, 500 lines, which is quite challenging for a scanning LiDAR solution. You see the lines here is the limit of the vertical resolution. Now let's talk about the basic problem you face when you do LiDAR systems. You have a car with a sensor illuminating the scenery, and by measuring the time of the light travels to the object and back to the camera, you can calculate the distance. But the reflected photons compete with the photons generated by the sun. And when there is full sunlight on the target, then you get a lot of photons back into your receiver. And the number of photons is a question of how long you have your shutter open. If you look to this diagram, you see that if you want to see 270 meters, you need a shutter opening time of 1.8 microseconds, 1,800 nanoseconds. Okay, during that time, you collect ambient light, so it's this on that level, let's say, and the integral under that linear line is the number of photons you collect from ambient light. Ambient light in general is not the problem. The problem is the shot noise, because light is particles which arrive statistically into the receiver, and because it's not a continuous flow, it's a fluctuating flow, you get shot noise. And the shot noise is generated, or let's say calculated here under this line area. This is the integral of the number of total ambient light photons and then the square root of that. So the square root of the ambient light photons is the shot noise. And it's obvious that a small pulse, which is smaller than the shot noise, it's, let's say, hard to detect, if it is possible. It's hard to detect because it competes with the stochastic shot noise. And going back to that slide, for example, if we collect in this 1.8 microsecond sampling time 4,500 ambient photons, they represent 67 ambient shot noise photons. So the fluctuation of this 4,500 on top is 67. So and if you want to do a simple detection of a pulse, you need typically a higher amplitude of the pulse. Basically, let's say 3 or 4 times. So let's say 10 to 12 decibel, and then you are in a good domain. So looking to that diagram again, if we collect 4,500 ambient light photons, then the shot noise is here 67 electrons. And to achieve a 12 decibel signal-to-noise ratio, you have to calculate that figure by 4, which is this one. So this curve shows how much light you need to be reflected from your object that you can do a reliable detection of the object. So that means about 270 photons. So quite a lot of photons are needed to detect a single pulse. There is one more problem to consider, which does not help in this respect. If you're looking to an object which is 90 meters away, the travel time of the light is 600 nanoseconds. And let's assume the pulse reflected is 100%. That's to normalize that at 90 meters. If we double the distance to the same object with the same reflectivity, we get just 25% of the light back because of the d1 to the d to the square formula. Or 270 meters, it's 3 times this. It's basically 10 times less, so about 10% of this signal. Okay, and now overlapping the pulses at various distances with the ambient light generated shot noise. And you see this pulse looks nicely out of the ambient light shot noise, but even this is already gone and this is gone again. So the shot noise competes heavily with the reflected pulse. So, and without a dramatic reduction of the shot noise, a single photon counting has no value, or let's say just little value, at least during daytime. And there are typically 2 ways to reduce the ambient light shot noise. Increase the laser power so that the shot noise is the same, but the reflected light power is higher, or reduce the measurement time. Reducing, let's say, the 1.8 microsecond shutter time to, let's say, 1 microsecond or 100 nanoseconds or even shorter. And because of a shorter shutter time, you collect less ambient light photons. And that's exactly what we do. We sample the incoming light into very short time slices. For example, 5 nanoseconds or 4 nanoseconds sampling time. And that means in such a sample, you get this multiplier compared to 1.8 microseconds of a full shutter time for the whole travel time to the, let's say, 5 nanoseconds. And here in this example, from 1.8 microseconds to 5 nanoseconds, the amount of ambient light photons is divided by 360. So much less ambient light photons. Okay, what are the requirements to do so? You need very fast CCD so that you can sample in that speed. Let's say, again, 5 nanosecond sampling time needs a 200 megahertz CCD. You need fast ADCs to sample that signal in. You need low noise receivers, and you need high quantum efficiency in the near infrared, which is typically used for such applications. And that's what we provide. It's our technology. We called OHC 15L. Some parameters here. It's monolithic CMOS CCD, which is a candidate for very low cost implementation. It provides a quantum efficiency of more than 70% at 905 nanometers. So very high quantum efficiency, not much loss in the conversion from photons to electrons. You need fast pixels. In our case, it's better than 7 nanoseconds. And you need a high conversion gain so that you get sensitive systems. We implemented here a conversion gain of 100 microvolts per electron. So 10 electrons already provide or produce 1 millivolt signal, which can nicely be sampled in a readout circuitry in an ADC. Okay, how we implemented our LiDAR systems. Let me compare the concept with a conveyor belt. So we have a conveyor belt here running in this direction. This is the starting point, and here's kind of a funnel where goods are dropped in. Now, let's start running the conveyor belt. We drop parts in, okay, and they arrive in a certain distance to the starting point. And this distance represents the time between we started the conveyor belt and the arrival time of the goods, right? If we know the speed, of course, we can calculate the distance. Okay? So we keep going, and the goods move all the way to the end and stop. So again, this distance is a time difference between start of the conveyor belt and the arrival time of the goods on the conveyor belt. Very simple. How to implement that electronically? The conveyor belt is a CCD, and a CCD is something that allows to get charge into a bucket and move it from stage to stage. That's what we do here. We have photons. They hit a photodiode in the pixel, and the pixel generates electrons, and the electrons are stored in a bucket on the CCD. So let it run. So the electrons here are now generated and stored onto the conveyor belt. We started the conveyor belt before they arrived, so the distance between the start of the conveyor belt and the location of the electrons is representing the time, how long it took for the light to travel to the scenery and back. Basically, when we start the conveyor belt, we fire the laser, right? And then the light goes out to the scenery, reflected back, and come to the conveyor belt, and they arrive in a certain distance to the start point. If there are multiple echoes, of course, they are behind each other and are nicely separated. Nicely separated, and we can measure the time to the first echo. It's this location, and the time to the second echo, which is this location. So basically, the concept is to translate the echo incoming time into a location on the CCD, like a sampling oscilloscope. That's the block diagram of the imager we implemented. Basically, this is the pixel field with the conveyor belt, readout circuitry, fast ADC, and then some LVDS channels. This imager is running extremely fast. So the CCD can run up to 250 megahertz, sampling in 4 nanosecond slices. There are 48 row ADCs in parallel, sampling each of them 3 rows. So the total number of rows here is 144 and 256 columns. And the data rate, the output data rate, if the data would not be filtered or, let's say, analyzed on the chip and data amount reduced just for useful information, it would be more than 30 gigabit of data, so a lot. And a circuitry here does a kind of an echo detection, packet generation, and then the imager sends up to 3 echoes per pixel to the host controller. Okay, a little bit more in detail how it is done. We have, as I said, photodiode charge detection. The conveyor belt for example, 400 buckets, a amplifier readout, charge readout, and analog to digital conversion. So, and the operation is in a way that we first initialize the conveyor belt, set everything to 0, and then fire the laser. The echo comes in and looks like this. So we get in every bucket a certain amount of charge. Okay, so let's continue here. So going back to the initial example, if we collect 4,500 ambient light electrons in 1.8 microseconds, when we sample that in 5 nanosecond buckets, we just collect 12.5 photons in one bucket. Okay, and the square root of 12.5 is 3.5. So the number of ambient light electrons collected is just 3.5 instead of 67. That means we can operate and detect pulses at the very low signal, roughly 12 or 14. It's actually 14 photons with a signal-to-noise ratio of 12 decibel. Okay, how is the imaging implemented? We have our pixel field in the imager with columns and rows. They are looking the same. The laser illumination is a vertical line which is swept over the pixel field on a MEMS mirror. And the controller selects the appropriate row where the laser is firing. So we fire a laser pulse, the laser goes into the scenery, echoes come back, are stored to the conveyor belt, and then in this frame store buffer. And here the echoes are read out. In the practical example, it looks like this. This is a portion of the imager. This is a distance, object is a distance of about 17 meters or so. You see the arrival of the pulse here or here. Actually, this curve shows this signal here. So you see some baseline, then goes up, number of electrons, and goes back. And this pulse represents the distance. The question is now, when you sample 4 nanoseconds, how accurate can you be? Because 4 nanoseconds means 60 centimeters resolution. But if you go ahead and use these values, the digitized values in this formula, which basically calculates the center of gravity of the pulse, you can achieve a resolution which is with 100 electrons, 12 centimeter resolution. If it's 1,000 electrons, it's then 1 centimeter or so resolution, just because of the calculation of the center of gravity. Okay. Operating distance we can achieve typically with these parameters here, 14 millimeters lens aperture, PD 0.5, 300 watt pulse, 5 nanosecond pulse. The reflectivity of the object is here, let's say 10%. We need about 20 electrons to trigger, and we achieved that at about 90 meters. So under full sunlight, 100K lux on the object. Okay, and this is the implementation, some pictures here. People, you see the resolution, and this is an image where we mapped people with an RGB camera to the scenery. The chip itself, the imager chip, allows frame rate of up to 312 frames per second, very fast, so that allows a lot of averaging or whatever processing. And we generate with this camera chip 10 million pixels per second. Okay, thank you very much for your attention.